Video 5.5, squares and their properties. So when we're dealing with these squares, we talked about a little bit in detail the properties that go along with them. But the thing that makes the square unique, if you remember, is that the fact that it doesn't have just one specific set of characteristics that makes it unique. It's unique because it has the characteristics of all the other kind of family of parallelogram shapes. So it's got all the properties of a parallelogram, it's got all the properties of a rectangle, it's got all the properties of a rhombus. So when you add them all up here, if you notice, you have a total of 10 properties that a square holds. So the fact that we have a proof dealing with a square, when we're told that we have a square like we do in this first one here, and we're given that it's square, that's a lot of information that they have given us in that statement. They gave us 10 pieces of information that we could potentially use. Obviously, we're not going to use all of those things, but there's a lot for us to be able to use. So deciphering through that into what's the best to use and all that kind of stuff will change based on the question and the type of information, but it just allows us a lot of opportunities to kind of get things. So let's do a little bit of practice here with this particular proof. So let me make my statement reason chart. And we're going to look at here. Again, if you don't want to start with the square because you feel like it's too much information, you don't know where to kind of go with it, there's nothing wrong with starting with one of the other figures. One of the other givens. But no matter what you do, I really do strongly recommend that you highlight what you're asked to find. And in this case, EG and FH are what I'm asked to show. Congruent. I look at that, and the first thing that pops into my mind is that, well, they are part of these two triangles, right? So if they're part of those two triangles, if I can show those triangles congruent, then I can say that the parts are equal using CPC-TC. So now again, that might not be the only way to do it, but that's the first thing that pops into my head, and that's how I would start off looking from here. So let's get into this information. I'm going to start with that first given, that we have a square of ABCD. And since it's a square, looking at the information that I see, I notice that I've got an alternate interior angle conversation going on here with this angle here and this angle here, which are inside of my two triangles. Because if AD and BC are parallel to each other, DB is a transversal, making those two blue angles alternate interior angles. So we can say here, first I have to state that I have parallel lines. So AD is parallel to BC, right? And that's because in a square, opposite sides are parallel, right? That's really the property that it comes out of because it's a parallelogram, right? And then we can make the claim that I'm going to call this angle 1 and angle 2, so it's easy to determine. Angle 1 is congruent to angle 2, and my reason would be parallel lines cut by a transversal form alternate interior angles that are congruent. And again, I'm abbreviating and using symbols, which is perfectly fine as long as you use the right symbols and abbreviations. All right, so what else can I do? So my next given here is I see both these statements tell me I got perpendicular lines. So I'm going to say that AD is perpendicular to EG and that BC is perpendicular to FH. And that's a given. And perpendicular lines means that I have right angles. So here I'm going to do these angles because those are the angles inside of my figure. And again, I'm going to call it 3 and 4. So angle 3 and angle 4 are right angles because perpendicular lines form right angles. And again, we're going to utilize that by saying that angle 3 is congruent to angle 4 because all right angles are congruent. Now the next one here, the next piece of information that's given to me is that DH and BG. So DH is all of this, right? All of this. Let me do it this way. All of this, and BG is all of this. Now those are not the sides of my triangles that I'm looking for, right? But they are including those things. So if I can kind of remove the part that is extra from both of them, we want to see if we can get the segments, right? So the fact that they both share that GH portion, and we're just going to move this on over here to make a little bit more space. I can then say that GH is congruent to itself because of reflexive property. And now I can use the addition postulate, the subtraction postulate to remove the GH part and only have the sides of the triangle BH and DG. So we can say the big part of DH minus HG, that's going to be congruent to BG minus GH. And if I do that, if I take away that, I'm just left with DG congruent to BH. Sorry, that kind of got a little crammed in there. And that was the subtraction postulate. And that specifically gets me this side and this side congruent to each other. And now we have three pieces of criteria. We just found a side. Angle 1 and angle 2 is an angle. Angle 3 and angle 4 is a second pair of angles. So now I've got two angles and one side. That side is only touching one of those angles. So we can now make the claim that triangle, I'm going to say DEG, is congruent to triangle. D matches up with B. E matches up with F. G matches up with H, and that's angle, angle, side is congruent to angle, angle, side. And last but not least, again, our whole goal here was to prove EG was congruent to FH, which as we started out, that's the sides of the two triangles we just proved. So EG is congruent to FH, and my reason would be CPCTC. And there we go. So there's our proof. It wasn't the shortest one, but there's a lot going on. But you can kind of see how a lot of things were inferred based on the information that we were given. So this proof had a lot that we had to do, but again, systematically go through each thing, utilize each given as best as humanly possible, and allowing you to formulate the parts that are needed for those individual pieces of criteria. All right. Let's look at our next question here. And it says that AC is 2x plus 4. So AC here is this one, which is 2x plus 4. And BD, they tell me here, is this part. That's 4x minus 2. So it's looking for what AC is. All right, so AC is that whole segment. So I'm going to start off by saying, well, these are diagonals, and they in a square, diagonals are congruent. So I can say that AC is congruent to BD. Therefore, 2x plus 4 has to equal 4x minus 2. This allows me to solve for x. So minus 2x over, I get 4 is equal to 2x minus 2. Add the 2 over. I get 6 is equal to 2x. If I divide both sides by 2, x will be 3. Again, that's not what I was asked to find. I was asked to find AC for part A. So AC is going to equal 2 times whatever x is, in this case 3, plus the 4. So AC equals, that's 6 plus 4, which is 10. The next part is DE. So I look over here and I see, well, DE is just this section, which is just from the vertice to the intersection of the diagonals. And again, in a square, because a square is a parallelogram, the diagonals bisect each other. So DE is just half of whatever DB is. And since DB and AC are the same, I can just simply say DB is 10. So therefore DE is half of that, which is 5. So now this is 5. And so we're looking at C here as our next part. It says, well, what's AD? That's this piece right here. Well, again, in a square, being able to identify the types of triangles we have inside of here, right? We've got a right angle here because the diagonals bisect each other, and we also know that the that the diagonals are perpendicular to each other, making the right angle. We also know that they bisect each other, so all of these segments are congruent, right? So if this one was 5, which I have as light blue, that means this part over here, AE, is also 5. So now I have a right triangle with 2 legs, and we're looking for the third. So I can call this X. Actually, I can't call it X because X has been defined. Let's call it a different letter. Let's use Y, right? Or I can just use AD as the name of the segment. But I can use Pythagorean Theorem to plug this in. My legs are 5 and 5. My hypotenuse, again, which is the side across from the right angle, I called it Y. So 25 plus 25 is equal to y squared. 50 equals y squared. If I take the square root to undo the squared part, I get y equals the square root of 50. It did ask for it in simplest radical form, so I do have to simplify my radical. If I take out the largest perfect square, that's going to be radical 25 times radical 2. Radical 25 is just 5. So therefore, AD is equal to 5 rad 2. If you got stuck on that, you could always use the radical and kind of use the factor tree method, where you break it up into all of its prime factors. And then for a square root, you look for pairs. Every time you find a pair of numbers that are the same, you pull it out and write it on the outside once, and then you just multiply anything that comes out together. But either way you do it, you should get 5 rad 2 as your answer. All right, just like some of the other ones, again, identifying, and we kind of just did it in this previous one, but what kind of triangle is ADC? Right, ADC right here is my green triangle, right? And again, we have a right angle here because it's a square. We also know that the sides are congruent, so that makes this a right isosceles triangle. So it's got 2 properties there that make it even more unique. AED, which is this one here, right? Again, diagonals bisect each other. So therefore these two, and are congruent, so those two are equal, and they are perpendicular to each other, so I have a right angle there. So I have another pair of right isosceles triangles. Now, because both of them are right isosceles triangles, and some of the other characteristics of a square, we can actually find all of these measures without being told anything, right? So I'm just going to do this. I'm going to label them in the picture rather than having to write each one of them down. But let's just look. So we already said, right, this angle here is 90 degrees, which means all four of these are 90. We also said that the big angles here at the corners of the square are all 90. And since the diagonals bisect the angles, or aka the diagonals are angle bisectors, half of 90, I mean, is 45. So each of these is not only 90 as a big thing, but each individual part is 45. And that's it. That's all of our angles. So there is, that little luxury, again, with the square, because we have so many details and the angle bisectors and perpendicular angles and everything. I don't have to be told. This is going to be true for any square that we have with diagonals. This will be true. No matter how big or small, the angle measures aren't going to change, but the side lengths will. So it's another good deal piece of fact to know. All right. So take the opportunity to look over the video. Anything in more detail that you need to go back and look over. And then take an opportunity to try some of this and see how you do.